Hello, my name is Ananda Suresh, and in this work, we would like to introduce our research work on optimization-free text-based image style transfer. Let me start off with a reminder of what style transfer is. It's a technique that merges two images into one. It applies the colors and textures, usually referred to as a style, of one image to the objects and the scenery or the content of another, creating a unique composite. In this example, you can see a new unique image created by the combination of the content image with the style of Van Gogh's Starry Night. Language-driven artistic style transfer, or LDAST, is an approach that eliminates the need for a style image by using a descriptive text instead, as you can see from here. In LDAST, the two leading approaches are CLIPstyler and Contrastive Language Visual Artist, or CLVA. CLIPstyler is an unsupervised method which uses a clip model to perform style transfer. It performs a lengthy optimization procedure at inference time, which can take up to a minute. In contrast, CLVA is a supervised approach that quickly stylizes image in milliseconds using a generalized model. However, while the CLIPstyler supports a broad range of input text, CLVA operates within a more limited scope. In this work, we aim to create a model that combines these particular strengths of both the models. We call this FastCLIPstyler. Before talking about FastCLIPstyler, let's start by briefly reviewing the background concepts that inform this model. First, I'd like to go over a work in style transfer from the purely vision domain. This model, which we refer to as the Gyasi style transfer model after one of the authors, is a generalized style transfer model that performs a task in a single forward pass. It consists of two models, a style prediction network, which converts a style image into a compact style vector, and a style application network, which is an image-to-image CNN that stylizes the content image based on the style vector. We use part of this model in our FastCLIPstyler framework. The clip model is another key background element. It's a pre-trained text-image embedding model that aligns a text phrase and an image within the same learned embedding space. This enables CLIP to calculate a meaningful distance between a text prompt and an image, effectively quantifying the degree to which the image corresponds to the text description. The CLIPstyler technique for style transfer uses this ability of CLIP to guide image stylization. CLIPstyler uses an image-to-image CNN that transforms the content image into a stylized one. It uses CLIP to compute the distance between the stylized image and a given text prompt. For a given text, the CNN is optimized while minimizing this loss until the resulting image is stylized as desired, which is a time-consuming process. We now introduce FastCLIPstyler. Over here, we show the architecture diagram of the model. As you can see, this is similar to that of CLIPstyler with few key differences. The CNN model that was previously optimized at runtime has been replaced by a pre-trained style application network. This network is directly taken from the Gyasi style transfer model. The idea is that instead of using a model that needs to be trained from scratch each time, we borrow a pre-trained model from the purely vision-based style transfer domain. In order to incorporate this style application network into the CLIPstyler framework, we introduce a text style prediction network. This is a compact feed-forward neural network that takes text embeddings as input and generates style embeddings. Rather than optimizing a large CNN from the ground up, we tune the smaller network for specific prompts using loss functions similar to that of CLIPstyler. This results in style embedding that conditions the pre-trained style application network to produce a final image. The loss functions required for this have largely been inspired from the CLIPstyler framework with some additions and deductions. Please see our paper for more details. This runs much faster than CLIPstyler because of the smaller size of the network that needs optimization. However, this approach doesn't eliminate the need for runtime optimization. It merely reduces the time required due to fewer parameters needing adjustment. To address this, we transform the challenge into a supervised learning problem. The aforementioned method is then used to essentially create a labeled dataset that facilitates this new learning approach. In order to create this, we collect a dataset of text prompts and run the optimization procedure on each of them independently. Once a model is optimized for a given prompt, the style embeddings corresponding to that is saved, essentially creating a mapping between text embedding and style embedding. We then take this dataset and simplify the problem into a simple supervised learning task where we train the text style prediction network on this dataset using a simple mean square loss. With enough data, this creates a generalized model that can stylize an image for a given text in a single forward pass. The inference pipeline looks like this. However, in order to do this, we require an initial dataset of text prompts. To create this, we first manually create sets of different symbol styles. We collect sets of colors, textures, art styles, and textured objects. We then combine them randomly to create various composite queries. We also take advantage of LLMs to create even more data. We give the LLM, in our case ChatGPT, examples of good style prompts taken from the Artemis dataset and ask it to provide us with even more examples similar to that. Using this strategy, we create a collection of around 5,500 text prompts that we use for training the model. In addition to introducing FastCLIPstyler, we also introduce a model that we call EdgeCLIPstyler. This is a variation of FastCLIPstyler with edge compatibility. The model relies on the key observation that the training of the text style prediction network does not rely on the text embedding sharing its latent space with image embeddings. This means that the CLIP embeddings can be replaced with a much smaller model for inference. Note that CLIP is still required for computing the loss function in the dataset generation phase, but for inference, we replace CLIP with a much smaller sentence BERT model. This makes the inference faster and leaves a smaller memory footprint, allowing the model to run on edge devices. Here we show how our model compares with the other state-of-the-art models. As you can see, both of our models are capable of image stylization similar to that of state-of-the-art. We would also like to specify some of the advantages that our model has over the other two. CLIPstyler is known to have a tendency to create undesirable artifacts throughout the image at times. Our model avoids this problem because the Gyasi model does not suffer from the same problem. Similarly, the CLVA model sometimes struggles to appropriately stylize images, especially when the prompt in question is very different from its training dataset. We avoid this problem because, again, the Gyasi model is known to have really good generalization. However, there are certain limitations to our model as well. For instance, CLVA often has better artistic quality to the images that it generates, while our model, on the other hand, tends to focus too much on just transferring colors and textures. Similarly, when compared to CLIPstyler, our model can be monochromatic at times. This is especially true when a color is implied either directly or indirectly in the given prompt. Here we show how the model scores according to various quantitative metrics, both automatic as well as according to a human survey that we conducted. As you can see, our models score highly across a lot of these dimensions. According to the human survey, FastCLIPstyler came out on top, with EdgeCLIPstyler coming in at second. While CLIPstyler produces impressive results in many cases, its scoring suffered due to overstylization and artifacts. Due to CLVA's inability to generalize to prompts outside its training distribution, it scored relatively low as well. Here we show the inference time for all the models in various devices. As expected, EdgeCLIPstyler performs the best across all of them. It's capable of producing images in milliseconds even without access to a GPU. On a very low-powered edge device like the Raspberry Pi, no other model was able to perform style transfer due to memory constraints. EdgeCLIPstyler, even though slow, did manage to perform there as well. Here, we showcase some more examples from our FastCLIPstyler model. In conclusion, we created a model that combines the best features from each of the state-of-the-art approaches in LDAST. Our model does not rely on an explicitly labeled dataset that needs to map prompts to images. It does this while remaining capable of performing stylization in a single forward pass, making inference to run in the order of milliseconds. It also shows impressive results on a wide range of prompts. Please let us know if you have any questions about our work. Thank you for listening.